I am going to kick things off today by talking about a set of projects that we call research design meets market design. Okay, our starting point in this work is the growing interest in approaching empirical questions from the perspective of as if ideal random experiments. So there's been a growth in lab experiments, field experiments, and search for natural experiments that has animated empirical work for the last couple of decades. And as we've seen in this course, experimental variation in industrial organization topics like that is relatively rare. So that makes theory play a much more important role. And theory is also quite important for extrapolation needed for many counterfactual questions. In matching markets, we're going to be using theory in a different way. And that is, we're going to be trying to figure out whether theory gives us any guidance on how exactly should we extract experimental variation due to tie breaking in centralized matching systems. Okay, so that's what my agenda is today. So our goal is to take data from a centralized assignment system and figure out how we would use that data to answer specific questions in a way that extracts experimental variation so that we can answer those questions in a way that's free of omitted variables bias. So a specific type of question is, what is the effect of being assigned a particular school? What is the effect of being assigned to your first choice school? And these questions are very specific. They would also play a role in asking maybe larger counterfactual questions where we need to think about some of the ideas you've been exposed to in this class, where we have to model demand and supply. But I want to focus today specifically on the narrow question of, given data from a centralized match, can I extract the quasi-experimental variation from that data? Okay, so yeah.
So in the last slide, so that by term, what is the effect? So what do you mean by that effect? What effects are we?
Yeah. So suppose I'm interested in asking what is the effect of going to a selective school on subsequent achievement. Okay, so what Nikhil talked about yesterday was evaluating matching systems by reveal preference, so measures like based on choices that people have made. And those allocative dimensions of assignment are surely important. You can think of this as trying to move towards productive dimensions of assignment. So is it actually good to send people to their first choice based on subsequent achievement outcomes or other things like that that we can measure? Okay, and I'll be very specific, so I have two examples that we're going to talk a lot about. But the key insight behind this work is that many centralized assignment mechanisms, like deferred acceptance that we saw yesterday, satisfy what's known as the equal treatment of equals property. Okay? What that is what it sounds like. An applicant who's got the same preferences and same priorities as another applicant, so we'll say preferences and priorities are an applicant's type, in a mechanism that satisfies the ETE property, will face the same probability distribution over assignments. Okay? And so because of tie breaking in deferred acceptance and similar mechanisms, we have a stratified randomized trial embedded in the mechanism. Okay? And so our goal today is to figure out how to make the most out of these randomized research designs embedded in the market clearing mechanism. Okay, and so I'm going to be talking about two specific papers today. So the first is studying the case where tie breaking is solely based on lotteries. Okay, and that's a paper that we just put out in Econometrica last year. And depending on how much time I have, I want to tell you about a new paper that extends some of those ideas for non-lottery tie breaking scenarios. Okay. And the first paper, the data we're going to look at is coming from Denver's Unified School Match. It's quite interesting in Denver because it's a district where all of the different school sectors have come together and said, why don't we have a common application, a single best offer system? And we'll be looking at charter school effects in Denver And the second application, we're going to be studying accountability systems used in New York City. And I'll tell you more about those as we get there, okay? And, you know, let me situate what we're doing here in terms of some earlier research. There is an extensive literature looking at data from centralized assignment systems to ask the types of questions that we're interested in. There's a set of papers that exploit the random tiebreaker scenario. There's a set of papers that exploit the non-random tiebreaking or regression discontinuity tiebreaker scenario. And our criticism of this literature, and you'll see my name is listed in both classes here, is that the papers here have wasted information. Okay? By not fully exploiting information contained in the mechanism, they are not learning as much as possible. And this is something that, you know, I think we've been struggling with for quite some time. I'll show you exactly what the gain of taking on the complexity of the mechanism is in terms of standard errors and precision gains later on. Okay? And the key concept that I'm heading towards is what we call the deferred acceptance propensity score. Okay? So the deferred acceptance propensity score, which I'll define shortly in our approach, is central. It identifies all of the random variation in school offers. Okay? So if we have a characterization of the deferred acceptance propensity score, we're going to identify scenarios that other research designs, like those that focus on schools people have ranked first only, what we call the first choice design, are going to be throwing away. Okay, and so that's one sense in which earlier work has wasted information in the data. The other thing that's important for us is the DA score we're going to give you an analytical formula for. Okay, and that's going to tell us exactly where random assignment is coming from. That's going to be seen to be valuable, especially in the second paper. Okay, so that's the introduction. Let me be very specific now about what we're trying to do here. Okay, so the research design pillar of this project works as follows. So let me define some notation. Let's let DI of S be an indicator for whether student I is offered a seat at school S. Okay, so it's a 1 if you're offered a seat at S, and it's 0 otherwise. And we will describe applicants based on their types. So that simply here is your preferences, your ranking of schools, and how the schools prioritize you. Okay. Now the problem is type affects assignment. Okay. So if I rank certain schools, I may be more likely to get assigned those schools, and therefore type is directly correlated with outcomes. Okay. So type is a powerful source of omitted variables bias. Okay, if we haven't adjusted for differences across applicant types. Yeah, question.
Type is what?
It's your preferences, your rank order list, cross your priorities at each of those choices. Okay, so it's a pretty high dimensional object. Okay, so one key theme here is we want to figure out how to reduce the dimensionality of the type. Okay. Now I mentioned deferred acceptance with lottery-based tiebreaking induces a stratified randomized control trial. So more specifically, if I have some covariate WI that's independent of lottery numbers, so you can think of this as a baseline covariate like your race or your baseline test scores. You can also think of this as your potential outcomes if you're assigned to a particular type of school. Because of the equal treatment of equals property, the conditional probability of being assigned to a given school, conditional on being an applicant of type theta, and this variable WI, your race, is going to be equal to the conditional probability where I drop the conditioning argument of race. Okay? Why is that? Well, race is not used as a factor in assignment. Okay? It's not part of the theta vector. It's not part of your preference or priority. So what this tells me is if I condition on applicant type, I will have eliminated any omitted variables bias in comparing applicants who are offered to those who are not offered. Put another way, if I have a data set of data from deferred acceptance linked to some, let's say, achievement outcome, one thing I could do is say, let's look at everyone who's ranked the same set of schools and who's got the same exact priority at each school, and look at comparisons within those cells. Okay? That would be a comparison for that type that would tell me what the effect of getting an offer is. that would be free of omitted variables bias. Now, what's the problem with this?
In this setting, what sorts of omitted variables do you have in mind?
It could be anything. So you might worry that if we don't have control for type, the types of families that are more likely to rank charter schools are more prone to gain from going to a charter school. It could be that the families that are higher achieving may be more likely to gain from going to a selective school. Right? So we want to figure out a way to neutralize that phenomena. That's the whole agenda here, actually. Okay. Yeah. Other questions? Yeah.
So as it's written there that WI might include the siblings, right?
So I want to make a distinction between theta and W. Okay. So theta is anything that determines your probability of assignment. Okay. So if I have a mechanism where I'm using sibling priority, I would put that in theta.
Then,
Okay. Great. Okay. So kind of our starting point would be, let's look at our data set, condition on applicants with the same value of theta, and look at contrasts by theta. Okay. Now, in a matching system, that's going to be impractical because theta is very high dimensional, right? So let's say we have data from Denver where there's applicants can rank up to 5 choices. We have 5 possible choices, cross priorities at each of those 5 possible choices, and you don't have many students with the same value of theta. Okay, so this is impractical. In fact, in Denver, of the 5,000 applicants who rank a charter school, there's 4,300 different types. Okay, so many types will have no one to whom to compare. Okay, so full type conditioning always works provided we have equal treatment of equals, but it's not a practical solution here. Okay, was there a question, Errol? Did you have a question? Theta is an individual characteristic. It's a ranking. So it's every applicant. So anything that determines your assignment risk is in theta. So that would be your ranking and your priorities. Just the assignment risk. So what's the distinction between theta and W? Given once I know theta, if I'm a black kid or not, depending on the priorities and the mechanism, now we can't use race, that won't determine my assignment risk, right? Okay.
so sir, then why we are interested in WI if it will not affect anything?
You're worried that so you're absolutely right. Given this property, you know, W is ignorable, right? So that's exactly the thing that we're going to leverage here, right? But we can only do that conditional on theta, okay? So if we didn't do this conditional on theta, we're back to the problem I just told Eric about. There are applicants who may have ranked more charter schools. And if we compare those to applicants who've ranked less charter schools, the difference in their outcomes could be a consequence of the fact that they ranked different sets of schools, not the actual effect of going to a charter school. Okay? We solved that problem by conditioning on theta. The problem is theta is high dimensional. It's not practical to condition on theta. Okay? So what are we going to do instead? What we're going to do instead is condition on a much lower dimensional object. Okay? And this is the propensity score. Okay? So the propensity score is simply the conditional probability of assignment to school S for an applicant of given type. Okay, so we've taken this high dimensional theta and projected it down to the scalar probability between 0 and 1. And the propensity score is valuable for us because of this following classical result from Rosenbaum and Rubin that states the following. Given the conditional independence property here, equation number 1, the theorem of Rosenbaum and Rubin states that conditional independence implies that for any Wi that is independent of lottery numbers, the probability that applicant I is assigned to school S conditional on Wi and the propensity score is equal to the probability dropping that conditioning Wi. Okay, so now Wi I can ignore. Okay. And a way to read this result, you know, this is always a mysterious result, I think, the first time you see this. Indeed, it's a one-line proof of this result is it is sufficient to condition on the propensity score to control omitted variables bias. Okay? And so why is this useful? For a couple of reasons. First is the dimensionality reduction. Okay? So the score is much coarser than theta. Even though individuals may have different preferences and priorities, they may face the same assignment risk. And I'll show you an example of that next. Okay? The next reason this is useful is the score is going to identify the maximal set of applicants who face non-degenerate risk, who are possibly randomly assigned to a given school, school S. And then finally, if we can characterize the score, we will have an expression that reveals the experimental design embedded in the matching mechanism. Okay? And that will teach us something about parameters. Where is the random assignment coming from? Okay? Now, one thing I want to emphasize here, you might have heard of the propensity score in some other contexts. So the propensity score is often discussed in research on observational studies, non-experimental studies, where you are willing to make strong assumptions like selection problems are only based on observables, right? We're not using the score in that sense, okay? I think that's not really an appealing use of the score. We actually have a random experiment here, okay? So, and we control the experiment because we control the matching system. We can replicate the experiment, okay? So the key thing for us with the score here is just this dimension reducing property and these other 2 points that I've mentioned here. So this is what I like to think is a much more appealing use of the propensity score than what's typically done in evaluation research. Okay, so let me show you some of the points that I just made in the context of a specific example here. Okay, so here I have an economy where there's 5 students, 1, 2, 3, 4, 5, and there's 3 schools, A, B, and C. Okay, and we'll suppose that each school has just 1 seat. The slide here shows the set of student preferences. Okay, so the way to read this is students 1 and 2 have the same preferences, A over B, and then the remaining students have different preferences. Okay, and we're going to suppose that the school priorities place student 2 as having a priority at B, so maybe they're a sibling priority or a walk zone priority, and student 5 has a priority at C. Okay. So what we see here is types are completely distinct. Okay, so there are no students who share a type. You might have thought students 1 and 2 have the same preferences, so are they the same type? They're not, because student 2 has a priority at B, whereas student 1 does not. Okay.
When you just have a single school for a student, that the student is interested in going to that school and only that school?
Correct, yeah, that's the way to read this, yeah. So exactly, so students 3 and 5 are saying, I like A, otherwise I'll leave the system, okay? So if I get a data set like this and I say, let's try to compare, let's say what is the effect of getting an offer at school A, the first thing I could do is look at my types and stratify on type and look at contrast within type, okay? That's going to be a non-starter here because all of the types are distinct, okay? So that's this point right here. The types are unique, so we cannot do full type conditioning. But here's an interesting fact about this example. If I run deferred acceptance with lottery tie breaking and tabulate the probability of assignment here, you'll see that deferred acceptance will assign students 1, 2, 3, and 4 to school A with identical probability of 1/4. Okay? And how can you see that? Well, the first thing I want you to note is student 5 here, the one that's not getting assigned to school A, is going to be ranking school C first, so he'll be proposing to school C. Student 5 has priority at school C, so he's going to get assigned to school C. No one is going to be able to displace him. Okay? So what does that mean for student 4? Well, student 4 actually likes C better than A, but there's no way student 4 can get C because student 5 will always get C. So we can effectively ignore the fact that he's ranked C first in terms of characterizing his assignment risk. Okay? And we're left in a problem where all 4 of the students are ranking school A first, effectively, okay, once we make this observation about student 4. And who's going to be assigned there? Well, there's no priority at A, so we have an even lottery, so whoever wins that lottery is going to be assigned there. And that's why the probability of assignment for the first 4 students is going to be equal at 1/4. Okay? So what we learn from this is if I do full type conditioning, I'm stuck. I can't do anything. If I condition on the propensity score for school A, I would have 4 students that I could possibly study. Okay? They face non-degenerate risk of being assigned to school A. Okay? So that's the first point about dimension reduction that we get here. Now, one other thing I want to make here is I can characterize a propensity score in this example because it's relatively simple, okay? In an example here with 5 students, we can actually tabulate all possible lottery outcomes. And with 5 students, we already have 5 factorial possible lottery outcomes. But this is simple enough. We can kind of reason through what's going to happen, right? You can easily see that in more realistic scenarios, that's not going to be straightforward to do analytically, okay? So let me move on to a second example, which works as follows. So here we have no priorities. There's 4 students. Student 1 only likes C, student 2 likes CBA, and then student 3 likes B over A, and student 4 likes A. So types, again, are unique, just as in the first example, okay? And so we can ask, what are the propensity scores? So again, full type conditioning is not going to work here. To compute the propensity score here, I would permute through all possible lottery draws, okay, and just tabulate your probability of being assigned to A, B, or C, okay? So here there's 4 students, there's 4 factorial or 24 possible assignments. So if I enumerate these assignments, I can figure out these conditional probabilities of being assigned school A for each of the 4 types of students. So some of these are much easier to reason through than others. So student 1 will never be assigned A. He's not ranking A, right? So his probability, his propensity score for A is simply 0, okay? Student 2 will get assigned to school A 2 out of the 24 draws. And when would that happen? What are those 2 out of 24 draws? Well, student 2 is ranking C first and then B first. So he's got to lose the competition at C, and he's got to lose the competition at B. How can that happen? That can happen when student 1 is ordered ahead of him, so beats him out at C, and when student 3 is ordered ahead of him, and so will beat him out at B. The next thing that has to happen also is student 2 is ordered ahead of student 4, okay? Because we want to assign student 2 to A, so he has to beat student 4 in the competition. So the orderings that I have to entertain here are 1, 3, 2, 4, and 3, 1, 2, 4, okay? So that's the 2 out of the 24 orderings, okay? Now you can see this is, somewhat involved to do, not that complicated. Student 3 is assigned to school A 1 out of 24 times, okay? And then student 4 is assigned to school A, the remaining probability, 21 out of 24 times, okay? So if you didn't follow this, you can just trust me on these calculations. There's a brute force way to do this. You can also reason through this. But what this example illustrates is even though I know the propensity scores here, I'm in a situation where there are no 2 applicant types who have the same value of the propensity score, okay? So there's no pooling here at all either, okay? So the propensity score is not even going to help me here in a finite market, okay? But let me show you something that, interesting that happens when I take this example and I replicate this example, okay? And I want to focus on applicant of type 2 and applicant of type 3, okay? So they have assignment probabilities that are relatively close. They're not exact, 1/12th and 1/24th. What happens when we go large, okay? And actually, so I can skip this. This is kind of reasoning through the different lottery draws to get to those probabilities. Here's a figure taking example 2 and just doing a type replication of it, okay? So I take each applicant of type 1 and make a copy of him, likewise for applicants of type 2, 3, and type 4. And on the x-axis here, I have the number of students of each type, okay? And what you see is the assignment probability for type 3 and type 4 applicants is different when n is equal to 1 in that finite example. We're comparing 1/12th to 1/24th. But as I replicate my economy, okay, the assignment probability of type 2 and type 3 applicants converge to one another, okay? So this is a very interesting fact for us, that when I look at the propensity score in a large economy, I get further pooling, okay? So if I think of a large economy as a good approximation of my data set, then there may be a justification for looking at propensity score values that are close. And you can also note that as soon as n gets to 4, doing this kind of tabulation is very, very costly. Okay, we have 4 different types of applicants. If there's 4 copies of each, that's 16 types of applicants. There's 16 factorial possible ways to order them. That's going to take a lot of time. Okay. Question? Yeah.
I'm a bit confused about how we're using the propensity score here. So
Mm-hmm.
but we seem to say that we don't know the preference ranking of the school.
No, it's in theta. So theta is your ranking and how the school ranks you.
But the way you were enumerating the probabilities earlier.
Yeah, so this is an example where there's no priorities, so that's why we can ignore that. In this example, we had priorities down here.
And so we're assuming that the school just has some random.
Exactly.
Anti-random.
In this specific example, in practice, of course, that's not true. So we're going to have to deal with that, right? So these two examples are just illustrative. Okay, the general problem is going to be much richer than this, but the 2 points I want to make, right? Just example one, we get coarsening, right, from the propensity score. Different types have the same propensity score. And example two is when we go large, we have different values of the propensity score converging to one another. Yeah. Question?
So the parodies are observable or?
Correct. Yeah. Yeah. We're going to assume the analyst can replicate the assignment process. Okay. Yeah. Okay. Okay. Terrific. Okay. So with those two examples out of the way, let me now move on to give you a formula for the deferred acceptance propensity score. Yeah.
You showed a nice convergence graph, but what's the intuition behind it, and how will we know if we have a result of that?
I will show you in just a second. That's where I'm headed. Okay. So we're going to be working in the large economy. We'll have theorems about convergence to the large economy. We're going to show you empirically that this is a reasonable approximation, the large economy. So that's exactly where I'm going. Yeah.
Should I ask you for intuition in this special case, in this specific simple case where you still remember it, or when you're
We're going to come back to it. And I'll even do this in data from Denver and convince you we have dealt with omitted variables bias in that setting. So let me move on and show you that. Okay, so what is the score concept that we're talking about? So we have deferred acceptance. We have lottery tie breaking in this project. So I want you to think about the score as the probability generated by the permutation distribution of lottery numbers. Okay, so what we've just done in the last two examples, this is a relative frequency generated by all possible lottery realizations. So in our data set in Denver, there's 26,000 applicants. So if we were to actually do this, that's going to take a long time. So, okay, so I'll get back to you. Now, of course, the law of large numbers tells us that it's enough to do this a sufficiently large number of times. We could sample from, 1,000 lotteries or a million lotteries, lottery draws. But we still have this problem of smoothing. Okay, so if we do a million lottery draws, tabulate your assignment probability across schools, the resulting empirical propensity score is going to then need to be smoothed. Okay, do we know that two different values of the score are actually the same score, or is that the actual sampling error? Okay, so simulation is always an option for us, but it's a bit of a black box option. So there's a smoothing issue, and there's also the question of where is the random assignment coming from. Okay. So what we want to head towards is a formula, okay? Can we give you a formula for the score? And we've seen that we can do that in these simple examples, but those examples are quite special. So aside from those examples, in any finite economy, we do not have a closed form for the propensity score generated by this permutation distribution with deferred acceptance. So that's why we're going to look at a continuum matching model, okay? And that continuum matching model provides several simplifications for us. So the first is in the continuum matching model, we can represent assignments in terms of a few easily computed statistics, okay, cutoffs in particular at particular schools. And you can think of this continuum model as a automatic coarsening or an automatic smoother. I'm going to take my continuum model score. I'm going to try to argue that that continuum model provides a reasonable approximation for my data set, okay? And I have to do no researcher discretion at that point. And I will show you that this provides balance in terms of treatment control contrast. And then finally, this thing that is also quite important, we're going to understand why there's random assignment. Okay, so one thing I'm heading towards, just to give you a flavor, is oftentimes, and I certainly made this mistake about a decade ago, you look at the data from a deferred acceptance assignment system and you'd say there's a school that has 100 seats and only 50 people are assigned there. You'd say there's no way there was a random assignment at that school. The school's undersubscribed. If we had an additional kid, he would have gotten in for sure, who would rank that school, right? And that turns out to be completely wrong, okay? Some of those 50 kids who are assigned to that school that has 100 seats could have been randomly assigned to that school by virtue of being rejected randomly at a higher ranked choice, okay? So in the course of the algorithm, when they apply to this school that appears to be undersubscribed, they will get in for sure, okay? But there's random assignment due to rejections at higher ranked choices, okay? And that observation actually allows us to extract much more information from deferred acceptance, okay? And I'll show you that actually helps us a lot in terms of the data.
How do you know how good an approximation the large market BA score is?
Yeah, so this is kind of an empirical question. That's the best I can give you. I'm going to give you different W's, different covariates, and I'm going to take my large market formula and say, let's do contrasts conditional on this formula of those W's. And like in most randomized trials, it's this balance analysis. If we really have a randomized trial, there should be no difference in observable characteristics between those who randomly got an offer and those who did not. Okay, so I will show you that we have, in the Denver data, very encouraging signs of balance. Okay, so another thing we've done in the paper, which is maybe closer to the theorem, is we've done this balance exercise by taking the Denver data and replicating it. And that's more of a simulation sense in which, when is this large market limit appropriate? And it works out pretty well, actually. So I think there's more work to be done on that specific topic, though. So we're using a particular large market limit here, this continuum limit. And the key feature of the continuum DA that we're exploiting is that in the continuum cutoffs, okay, the last kid to get into a school, the assignment cutoff, and I'll define that in a sec, are fixed, okay? In a finite version of deferred acceptance, cutoffs could be moving around. If I have a different lottery draw, the cutoff used at a particular school could go up or down by a little bit, but somehow that converges very quickly to a constant. And there are some formal results about this. Actually, Nikhil has some results about this, and Azevedo and Leshno have some results about that. That's the key thing that we're exploiting here that makes this work. Yeah. Mm-hmm.
So to get assigned randomly to an undersubscribed school, do I have to rank it somewhere in my preferences, or
Yeah.
I do have to rank
You
it?
do have to rank it. Yeah. Yeah. Yeah.
If I ranked, like, so I ranked only one school, is there a law that still forces me to go to some school?
It depends on the city. That's a really good question. So, you know, what we can control is the offer process, right? You have the inputs, they run deferred acceptance, they send letters saying this is your offer. What you're asking about is, once I get an offer, do I have to go there, right? And in some cities, if I don't want to take my offer, I have to go through a formal process to switch assignments. So that, for instance, in New York City is controlled by the central office. In other cities, like in Denver, that is controlled at the school. So that's where there's a lot of room for non-compliance. So what ends up happening in cities like Denver is, I don't get into a charter school. I really want to go there. I engage in this active lobbying effort over the summer, and sometimes I can convince my way in. Okay, that's not a real problem for us here, because we're going to be using the offers as our source of random variation. Okay, and we will solve this partial compliance problem using instrumental variables. So that's the usual way people deal with this.
It's like a different thing. Can I go to no school? So, for example,
So
in country, you can't.
Yeah, in the U.S., you're required to go to school till age 16. So
You could go to a private school.
you could go to a private school for sure. Yeah. So so we'll talk about that. So that's another challenge. Often that's not the real focus here, but you're worried that there's differential follow-up between those in your sample. If I don't get my first choice, I say I'm out of here. I'm going to private school. You don't see many issues on that in these kinds of markets, because we typically focus on applicants who apply from public school at baseline. So the attrition problems really appear when you have a child applying from private school. They say, look, I'm going to go to this great school if I get in, otherwise I'm going to stay at my private school. So the follow-up differentials here are in the order of 1 or 2%. That's not your question. Okay, what's your question?
I listed only, imagine a situation, I listed only one public school.
Yeah.
I don't get there, private or charter school.
Okay.
What happens next?
So first of all, charter schools are free, so you don't need money for that. Okay, that's a common misconception. What happens next? The processes differ by city, but broadly speaking, there's an administrative process where they will call you up and say, you didn't get your choice, you have to go to school. We're going to assign you to the school that's closest to where you live. Okay? And so you can then say, I'm not going to go to school. Okay? If you're that kind of kid, then you're in trouble. There's disciplinary proceedings and things like that. If you are under age 16, if you're 16, we can't do anything to you. Yeah, that's how it works in the U.S.
Is it concerned in data?
I'm sorry?
Is it concerned in data?
No, not at all. So follow-up differentials here on the order of 1 or 2%, which is really good as far as these studies go. Yeah. So and that's again because we're starting from kids at baseline in public school. Yeah. Mm-hmm.
So just your comment on this propensity score.
Yeah.
Computing that for TTC will be easier, or we can't
That's
say that
another great question. Actually, that is an open question. Okay. So no one knows how to do this. So top trading cycles, one of the important mechanisms I talked about yesterday. If I wanted to do this exercise for TTC, no one knows how to do that yet. Okay. And part of the challenge is giving you a model for top trading cycles in the continuum. Okay. So there's a very recent paper that gives a version of that model in the continuum. It's a little bit of an indirect characterization, but it's not there's a lot more work to be done to get to a formula like this. So what we're trying to do mathematically here is just get a formula for the conditional probability of assignment given your preferences and priorities, right? So you can definitely ask this question for other assignment mechanisms. So yesterday I talked about serial dictatorship. That's a special case of deferred acceptance, right, where the schools are ranking everyone in the same way. So these results will apply here. The Boston mechanism, which I talked about yesterday, that can also be expressed as deferred acceptance. How do we do that? Well, we modify the priorities of schools to have people who've ranked a school higher get more priority than people who ranked it lower, and then we implement it via deferred acceptance. So those mechanisms are handled by what we're going to talk about today. Yeah, great. Okay, perfect. So let me now get into a bit more formalities, and I have to do a little bit of notation. So I hope there'll be a payoff of this later. So in my model here, I have I students with preferences and priorities. We're going to encode the priorities as integers, okay, from 1 to k, and infinity means you're ineligible for a school. So row IS is the priority of student I at school S. A student's type now, more formally, is their preferences and their priority vector, okay? Row I, the priority at each of the schools. We have S schools, and they have capacity given by QS. And we're working with a continuum model, so you can think of the set of students as an interval, and the capacity is the proportion of the students that can be seated at school S. In the lottery case, we're going to start off by assuming that there is a student-specific lottery number. So that's denoted by RI. And that's IID uniform from 0 to 1. And an student's rank at a given school is going to be given by this pi IS. Okay, student I's rank at school S is going to be their priority, the integer part at school S, plus the lottery part, which is between 0 and 1. Okay. And in the continuum model, we can express the DA assignment as follows. We have a vector of cutoffs for each school, CS, and an applicant will be assigned to school S if their priority is less than or equal to the cutoff at school S, and their applicant rank pi IS is greater than the cutoffs for all higher ranked schools. Okay, so you are assigned to the highest ranked school for which you qualify, okay, for which you are below the cutoff. Now, where do the lottery numbers play a role here? So the lottery numbers only matter for assignment within what we call the marginal priority group. Okay, so let me make that clearer with the following example. Okay, so here I have a school, and I have a set of applicants who are at the school. Their rank here is simply the priority row plus the lottery number RI. Okay, so the first applicant's rank is 1.13, so that's just 1 plus 0.13. And I've sorted these applicants by their rank. So in our data set, we'll see that an applicant with a rank of 2.35 is the last applicant to get into the school. So that's going to determine the cutoff at the school. And now what is the marginal priority? Well, where does the lottery number actually matter? Well, any applicant who's in the first priority group is going to get into the school for sure. Any applicant who's in the third priority group is not going to get into the school at all. So our rationing is taking place within priority group number 2. So that's why we call this the marginal priority group. And it's helpful to describe the cutoff, the lottery cutoff within the marginal priority group. That's what we call tau s here as simply 0.35. Okay. And so now, how am I going to give you a formula for the deferred acceptance propensity score in this continuum model? I have the primitives on the student side set up, the priorities and the cutoffs. Let me now partition my applicants based on their types. And I'm going to split applicants into 3 groups. Okay, so take applicants who've ranked school S and put them in capital theta S. And let's let B of theta S be the set of schools that an applicant of type theta likes better than school S, okay? That they prefer to school S. Looking at those applicants, we can split them into 3 groups. The first group are what we call the never seeded, okay? So never seeded is what it sounds like. These are applicants who have worse than marginal priority at school S. So in that last table, these are applicants in priority group 3, okay? No one in this group will be seated at school S, okay? So that's what this notation reflects. Okay, your priority of type theta at school S is greater than rho S. That's the marginal priority group at school S. Okay. The second group I want to introduce is the always seated group. Okay, so that is the applicants in priority group 1 in the previous table. Okay, these are applicants who will be seated at school S provided they're not assigned to a school that they've ranked higher. Okay, so provided they are not seated at a school in a B of theta S. Okay, and the group that is of interest to us, maybe most interest to us, are the conditionally seated applicants. Those are the applicants who are in the marginal priority group at school S. They will get in only if they clear the lottery cutoff for that group, right? So members of this group will be seated if they're not assigned something more preferred and they clear the lottery cutoff. Okay. So that's my partition of applicants. The last object I want to introduce, okay, and then I will give you the formula, is the maybe the central idea that we want to deal with. We call this the most informative disqualification. Okay, so what are we worried about at a high level? We're worried about censoring in the lottery number distribution that comes about by your rank order list. Okay, so if Eric has ranked school A first, and I've ranked school A 10th, or 12th, okay, that's what we did yesterday, right? When Eric applies to school A, his lottery number draw is going to come from the full support of the distribution, from 0 to 1, right? When I apply to school A 12th, I'm going to have been rejected from my choices 1 through 11. So my lottery numbers may not be coming from that full support because I've been rejected from higher ranked choices, okay? The fact that I've been rejected from higher ranked choices means my lottery number is pretty bad, right? I didn't qualify, I didn't win the competition, so my lottery number is censored, and we want to figure out a way to characterize that censoring. Okay, so that's what the most informative disqualification is giving us notation for. Yeah, is there a question?
Your priority rank independent across schools?
Yes. So I also have to deal with the fact that maybe I didn't get into my top 11 choices because I was, in the never accept group or in the conditional accept group. So that's right. So in the simple example where there are no priorities, what do I know? If I didn't get into my top 11 choices, what I would do is, no priorities, easy case, I would say, what is the most forgiving school that I did not get into? What is the school that's got the highest cutoff that I did not get into? Okay, so I look at all of my 11 choices and I say, well, maybe it was my 7th choice that was the easiest to get into, that I didn't get into. What does that mean about my lottery number? That means my lottery number is actually worse than the cutoff at that school. I didn't get into that school, right? So what's important about that is once I know I didn't get into that easy school, I don't need to worry about the other schools that I've ranked, okay? So that's why it's the most informative disqualification, okay? That's what we're going after. Now, your question was, what about priorities, okay? So I have to now qualify what I just said by looking at schools for which I'm in the marginal priority group and do that same kind of exercise, okay? So let me explain this yet another way. So the formula for the mid looks a little bit scary, but this is what's going on here, okay? So there's three different cases. The first case is kind of the easiest. So suppose my priority status as a type theta applicant for all schools that I've ranked above S tilde, okay, all of the schools S tilde in my better than set, is such that I'm worse than marginal at all of those higher ranked schools, okay? Then there is no information in the fact that I've been rejected from those schools because I had no chance of getting in. I wasn't in the marginal priority group. My priority was too low. So there's no censoring we need to deal with in this case, okay? So your mid is exactly equal to 0. What about the second case? The second case is a case where at a school that is ranked above school S tilde, I'm in a priority group where I'm always accepted, okay? In that case, there is complete truncation. There's no way I'm going to compete for school S because I will have been assigned to a higher ranked school for sure, okay? So that's the second case that is simple. So first case, no truncation. Second case, complete truncation. The third case is the more interesting case. So what we'll do here is look at your higher ranked choices. We'll look at the set of schools for which you're in the marginal priority group. So S tilde higher ranked choices in my better than set. The schools for which my priority is the marginal priority, and look for the maximum cutoff in that set. Okay? So in words, let's say Eric has ranked something first, I've ranked something 12th. I'd look at all of my higher ranked choices and say, which of those higher ranked choices am I in the marginal priority group for? Okay? So let's say it's a handful of them. And then what is the largest cutoff of those? Okay? And again, the whole point is I only need to worry about the largest cutoff because if I've been rejected from that easy to get into school, I will have been rejected from other schools as well. Okay? So that's what this third case is dealing with for here. So most informative disqualification is the most forgiving cutoff at the set of schools for which you're marginal. Okay? Okay, so that is all the ingredients that go into the formula for the propensity score. Okay, so in our continuum economy, we can characterize the propensity score as follows. My propensity score for an applicant of type theta at school S is 0 if I'm in the never accept group, if I'm always below the marginal priority group. If I'm in the always accept group, my propensity score at that school is equal to 1 minus the mid. Okay? So what's going on in this case? Well, by the time in the algorithm I get to apply to school S, I will be always accepted, so I get in for sure. Okay? So the only way I can be randomly assigned to school S is by being rejected from higher ranked choices. Okay? And the probability that I get rejected from higher ranked choices is going to be 1 minus the mid. Okay? The last case now takes these the case where I'm a conditionally assigned student at school S. So in the algorithm, when I apply to the school, I'm in the marginal priority group at school S. And what do we have to deal with here? So there's two terms. The first term is that same expression dealing with the fact that I've been rejected from higher ranked choices. Okay, so that's the 1 minus mid term. The second term is the probability of being assigned this school conditional on the fact that my lottery number has been truncated. Okay, so this is a conditional probability. That's why it's 1 minus mid in the denominator of being assigned school S. Okay, great. So what's nice about this formula is in the continuum, the mid is a function, is a cutoff, right? The tau is a cutoff, and the thetas are all going to be fixed. Okay. So our second theorem, which I won't state for you on the slides, states that the sample analog of this, so I have a finitely sampled economy, I take the limit as n gets large, will converge uniformly to the finite market propensity score as the market size grows. Okay, so that's a justification for using this in a real applied problem. Okay, so let me now go back to the example and show you the magic of this formula, okay, in action. Okay, so what did we see in example 2? We saw that applicants of type 2 and type 3 had the same continuum propensity score when I simulated that example out, right? I let n get large and they both became 1/12, I think it was, right? So how does that play out here? Let's go through the reasoning here. Okay, so in this economy, there's no priorities. Again, we're keeping this simple. So what are the cutoffs going to be in the continuum? Okay, well, one way I can think about this is looking at the demand here. So I'm going to try to reason through this. So student 1 and student 2 are the only students competing for school C. As I have more and more types of student 1 and student 2, we're going to basically split school C in half, okay, between type 1 and type 2. So the cutoff at school C is going to be exactly a half, okay? And in the continuum. Now, what about at school B? Well, I'll have used up a half of school C, and it'll run out in the continuum. At that point, a half of B will be gone. Then next, the remaining type 2 applicants will want to compete for B, okay? So the cutoff at school B is going to be 0.75, okay? So, so that's where these cutoffs come from. If anyone is familiar, how am I doing this so quickly? Okay, so there are results that we can express the continuum version of this problem as a mechanism called probabilistic serial. So that provides a shortcut to get these cutoffs, for those of you who know what I'm talking about. If you don't know what I'm talking about, that's fine. You can just trust me and say these are the cutoffs in the continuum, okay? Great. Okay, this is just intended to be illustrative, okay? So the next step in the calculation is let's look at the better than sets for type 2 applicants and type 3 applicants. What schools are better than A for type 2? Well, B and C. What school is better than A for type 3? That's just simply going to be B, okay? So then what do I do next? I compute my most informative disqualification. So for an applicant of type 2, I look at my better than set, school B and school C, and say, what is the most forgiving cutoff? Okay, so the cutoff at B is 0.75, the cutoff at C is 0.5. The most forgiving cutoff, therefore, is 0.75, okay? And that turns out to be the same most informative disqualification for a student of type 3, okay? The mid for student 3, we look at his better than set, it's just school B, the cutoff at school B is 0.75, okay? And that is going to be the essence of why we can pool these two guys together, okay? The information contained in the fact that student 2 and 3 have both ranked B dominates for student 2 the fact that they've also ranked C, okay? Because B is more forgiving than C, okay? So we can conclude by our formula that types 2 and 3 will have the same large market score at school A. And how would we then compute that object? Well, we go back to our formula. So our formula here, I have the mids, right? The only thing that remains to be computed is the tau at school A, okay? And let me just assert that that cutoff is equal to 5/6, okay? So I go to my formula, I have 5/6 minus the mid of 0.75, and I get 1/12, okay? So that's explaining where that figure comes from, why it's exactly equal to 1/12, okay? And why we get this pooling. Okay, the most informative disqualification here is B for students of type 2 and type 3. Okay, so that's what we learned about the mechanism. Now, let's try to put this to use and try to learn something about school effects in Denver, okay? And so there's a couple of implementation issues that I want to just kind of briefly mention. Once I have this formula, there are a couple of ways I can go. Oh, question, yeah? I'm sorry? These are in the paper, yeah, exactly, yeah, yeah. Okay, great. So how am I going to take this formula and actually estimate the quantities here? There's two different approaches we could take. I look at my data set. I look at that priority table that we just saw with each school. I partition applicants into the never accept, always accept, and the conditionally accept. I look at the empirical cutoffs. That gives me the mids. And I can compute the score by just looking at those quantities exactly. Another thing I could do is take this exact process, this formula, and then within folks that have the same exact formula score, just tabulate the empirical offer rate. How many kids with the same exact formula score got an offer and did not get an offer at a given school? Okay, so these are two different ways to do this. The third thing I'm going to show you is just simulating the finite market score. So I'm going to do this 1,000,000 times. What we're going to do for 1,000,000 times, just one point to make is, as the number of lottery draws increase, this will converge to the finite market score. But we don't get any dimension reduction even with 1,000,000 times. So you have to do some kind of smoothing. Okay, so we're going to round the score to, I think I'll show you numbers from rounding to 1,000. Okay. Great. Okay, so now let me tell you a bit about Denver. Okay, so Denver is one of the pioneering cities that took traditional public schools and charter schools and put them under one umbrella for assignment. Okay, so what is a charter school? Just by way of background, a charter school is a publicly funded school that operates out of traditional district rules. Okay, so they have a lot of autonomy in hiring and firing. In Denver and in most places, charter school teachers are not part of collective bargaining agreements. And they are one of the most popular education reforms in the United States. So about 5% of kids in the US now go to a charter school. Okay? And we are interested in showcasing our technology here using data from the unified match in Denver. So Denver uses deferred acceptance where children can rank up to 5 schools. And there's lottery tie breaking. And our question is, what is the effect of getting assigned to a charter school for the applicants who've ranked those schools? So how do I put this formula to work? Let me define DI to be a dummy variable that indicates you have been offered a seat at any charter school. So we're going to start off looking at pretty aggregate charter sector level effects. What is the effect of charter versus not charter, okay? And then we're going to make this more and more fine-grained as we proceed. Now, how do I deal with this aggregation issue? I gave you a formula for the propensity score for a given school to say what is the propensity score for being assigned a charter school. I would take an applicant of type theta and compute of all the schools they've ranked, which are charter schools, what is your p-score for each of those charter schools, and sum them up, okay? So a child could face non-degenerate risk at their first choice charter school, but if you look at their second choice charter school, they get in for sure. In that case, they would have a propensity score of 1, and they would not be subject to random assignment. Okay, so this is what this aggregation step is doing. And finally, our mediator is going to be an enrollment. That's going to be our endogenous variable. CI indicates did you enroll in a charter school following assignment. Okay, and so the way we're going to marginalize this, so all of our results are for a given theta. Okay, so I'm giving you a way to tease out the effect for a given actual value of the propensity score of getting an offer at a charter school versus not a charter school. If I showed you that for all possible values of the propensity score, that's going to just be a ton of numbers. So we have to find a way to then aggregate across values of the propensity score. So I'm going to do that using a simple 2-stage least squares weighting system. Okay, so my setup is the following. My first stage is going to project charter enrollment CI on the instrument here, the charter offer dummy, DI, and I will have dummies DIX for propensity score values. Okay, so I use my formula, I look at all the values of the propensity score, and I dummy those all out. Okay. And then my second stage is going to have my endogenous variable of charter enrollment with the same exact propensity score controls. Okay, let me see how we're doing. Let me skip this issue for now, and let's actually look at some data here. Okay, so question, yeah, Ori. Yeah, so what, yeah, that's a, yeah, so what my theory gives me is the effect for applicants who have the same propensity score, okay?
But we're assuming now we're affecting the identical effect on all, regardless of the propensity.
We're not doing that. I'm allowing that to differ by values of the propensity score, and I'm taking a weighted average of that, okay? The particular functional form that's allowing me to weight across different values of the score is coming from this 2-stage least square system. You could be less parametric about that. Actually, we do that in the paper. So this is kind of semi-parametric weighting across the propensity score. The estimates are pretty similar, actually.
Should I think of it as the usual average effect? I'm just having a hard time.
All right, so let's Yeah, sure.
So, in order to figure out who it helps, you have to figure out which utility functions map into that propensity score.
You know, one thing I can say to be very precise, Ori, is I'm giving you the local average treatment effect for values of the propensity score being in common. Okay? So what does that mean? That means for the set of people who've applied to a school and whose enrollment status is affected by this instrument. Okay? On top of that, I want to give you one number. I don't want to give you that number for all values of the propensity score. I have to take some weighted average. Okay? So I'm going to keep it simple for now. The paper does some additional work on that. Now to Ariel's question, okay, so what does this parameter tell me about? In this setting, we have a setting of effectively one-sided non-compliance. Okay, so if you get an offer at a charter school, basically it's a setting where there's very little defiance. Okay, so it's not the case that children who get an offer at a charter school are less likely to go to the charter school, and vice versa. Children who don't get an offer are more likely to go. So you can interpret this specifically as an estimate of the effect of a charter school on those who've applied, or what we would call a treatment on the treated effect. Okay, so that's a very well-defined question. And if you wanted to think about normative issues like Ariel is suggesting, you would have to make further assumptions. Okay, so we're going to keep it simple for now. But if you wanted, as a policymaker, to say, what did Denver's charter schools do for its applicants? This would be the attempt at answering that. Okay. Okay, great. So let me show you some other things. Okay. So and you know, Ariel and I have been having this conversation for like 3 years now. So that's why I'm raising my voice here. Okay. If you wanted to ask some of Ariel's questions, okay, I think the way to proceed would be to take, as I said in the first slide, what we've done here and use some of the stuff Ariel talked about at the beginning of this course to think about what made people rank certain types of charter schools. So something I'm not able to answer without further assumptions here is what would happen if we opened up a new charter school? Okay, that's a new policy question. That's outside of the scope of what we're doing here. But that's now, I think, answerable in a more credible way, given we have a very good estimate of the existing charter schools. Okay, so all right, so back to the numbers here. Okay, so I still have never convinced Ariel on this, but that's what makes this fun. Let me show you some. Let me show you some facts. Okay, I have a list of all the charter schools in Denver on this table, and I'm showing you the number of applicants who are offered seats. And let's just focus on column 3. So these are actually, let's focus on column 4. These are the kids who have non-degenerate propensity scores, who face random assignment at the school. And I want to compare that to column 6 here. Column 6 are the folks who faced a non-degenerate random assignment, non-degenerate propensity scores at the school, if we only looked at first choices. Okay, so this was kind of the state of play prior to this work, looking just at first choices. And you see a lot of the schools have zeros here, which means I could not study these schools using the experimental variation if I just looked at first choices. Okay, in column 4, on the other hand, when I look at the formula that we just talked about, every school but one has randomly assigned kids. Okay, so this is one sense in which we have much more information from the match. Okay, so the one school actually that doesn't have random assignment is the Denver Language School. It turns out no one was even offered a seat at that school that year. They actually went on to close that school. And another way to see this is if I look at the non-charter sector, each point here corresponds to a school. The black points are the number of applicants who are subject to randomization if we just look at their first choice. The red points are the number of additional applicants subject to randomization using our method here. Okay, so we're getting much more data out of this process. And why is that? I mean, one thing that I mentioned earlier is this idea that you can be randomly assigned to a school by virtue of being rejected at a higher ranked choice. Okay, and a particularly stark version of that comes out in the example of Strive Prep. Okay, so this is a pretty noteworthy charter school in Denver. They operate 6 different campuses: Strive Green Valley Ranch, all the way down to Strive Westwood. And what you see here is a partition of applicants to these schools. Okay, so there is a group of applicants here who have a score of 0, so they're not randomly assigned to that school. In column 6, you see most of these applicants are always accept applicants. So what does that mean? That means that they've ranked a higher rank choice for which they are going to get into for sure. Okay? So when they go on to apply to a Strive campus, they face no risk, okay, because they got into the higher rank choice for sure. Okay? So that's why their score is exactly equal to 0. If I jump over here to the last column, we have applicants who are getting into a Strive campus for sure. These are applicants that when they apply to Strive, they are in the always accept group. Okay, they're above the marginal priority group at that school. So there's no rationing that's taking place for them. They're going to get into the school for sure. The interesting group here are columns 7 and 8. In columns 7 and 8, you see two contrasts. Okay, for the first 4 Strive campuses, the number of applicants who are conditionally seated, the guys in the conditional set, is exactly equal to 0. Okay, so what's interesting about this is for the first 4 Strive schools, random assignment is not coming from when you apply to the school, you randomly get in or don't get in. It's coming from the fact that you're randomly rejected from a higher rank choice. Okay, so these are guys who are always accept at the Strive school. When they apply to the school, they'll get in for sure. But they still face random assignment because they were randomly rejected from a higher rank choice. Okay, so we're getting to study all these additional kids you wouldn't have studied without dealing with this method. In the last 2 rows here, you see the kind of, I think, expected case. There's random assignment at the point at which you apply to the school. So, okay, let me press ahead here. So, in terms of our data, one interesting thing about Denver is it's a high Hispanic share. So relative to other studies of school effects, we typically don't see about 60% of the applicants in the school choice system are Hispanic. Most of the work like this has been focused on Northeast school districts where it's more black than Hispanic. If you look at the contrast between columns 1, 2, and 3, column 1 is all Denver students. Column 2 are those who applied in the match. Column 3 are those who applied to a charter school in the match. What you see is that the characteristics are quite similar as you go across the columns. And I think that's one dividend of having a centralized assignment system. So typically in studies of charter schools, we see this positive selection that the types of kids who apply to charter schools are those who are in the know, whose parents figured out there's a lottery night. And in a unified match, everyone has to apply through the same process. So the patterns are much more representative. For instance, in our work in Boston, if you look at the baseline score contrast between applicants and your underlying match participants, it's about a 0.1 standard deviation difference. And here, it's a much smaller difference. Okay, yeah.
Why so many Hispanic students?
Yeah, so that's the Denver population. So Denver has a high Hispanic share in the public schools. Okay, let me press ahead. The next thing I want to show you is, did this formula actually work? Okay, so this was Eric's earlier question. The way I'm going to show you this is I'm going to take characteristics of applicants and condition on my propensity score formula. Okay, so let's just focus here on column 4. What this column represents is the difference in the number of schools ranked, or the number of charter schools ranked, or whether your first choice is a charter. For those who are offered versus those who are not offered. In column 4, I've controlled for my propensity score. In column 1, I have no controls. So if I looked at column 1, I would say I have a biased comparison, right? The kids who have gotten offers to a charter school are, for instance, ranking on average 0.47 more charter schools than the kids who do not get an offer. However, once I condition on the score, that contrast goes away. Okay, so I have a well-controlled comparison now using my formula. And I still have a fair amount of data, 1,200 kids. If I were to do that using full type control for theta directly, my sample size is just 301 kids. Okay, and now table 6. So this is the estimate of charter effects. And here, this kind of goes to Ori's question. So how am I aggregating across different score values? The semi-parametric columns here are a way to do aggregation that differs in 2-stage least scores. What you want to take from this is there's not much difference in the weighting here. what that suggests is we don't have much power to detect differences in treatment effects by propensity score, actually, okay? Let's just focus on math. So the effect in the very first column of getting a charter offer, the effect of charter enrollment on your standardized math performance is about 0.5 standard deviations, okay? So that is the effect of Denver's charter sector. That's an enormous effect, okay? You know, prior to the research on charter schools, we never saw any school-level interventions producing effects this large on standardized test scores, okay? The typical way to benchmark this is in the United States, the black-white achievement gap is about 0.8 standard deviations, okay? So this is saying getting charter exposure for 1 year is making a large enough difference to cut the black-white achievement gap in half, okay? So that's one reason people are quite excited about the charter sector, okay? Now, let me look at, you know, these patterns of selection and what would have happened if we had just done OLS, or what exactly are we gaining from the propensity score. So let's just focus on the math effect again. If I had just done OLS, you would have a biased estimate of 0.3 relative to the two-stage least squares estimate of 0.5, 0.496. Some of that bias gets knocked out by putting score controls, by putting propensity score controls, so, but not all of it, okay? So these are important points to make here about why we need to have the propensity score formula correctly specified. Now, let me show you a couple other things we can do with this. So far we started simple, charter versus non-charter. Let's see if we can unpack this, okay? So when we look at the contrast between charter and non-charter, let me come to you in just 1 second. So let me tell you a bit about what happens to kids who do not go to a charter school, okay? So focus here on the last column. The kids who do not go to a charter school, about 50% of them go to a traditional public school. About 33% go to what's called an innovation school. So that you can think of this as a charter school that's operated by the district, so they have some freedom from the collective bargaining agreements that traditional public schools have. About 10% go to a magnet school, okay? So let's take our machinery and try to decompose the charter-non-charter contrast by estimating sector-specific models, okay? And eventually what we'd like to do, and we haven't quite figured out whether we'll have the power to do this, is to get to a school-level effect, okay? So get to a school-by-school effect. Sectors are a step towards that. So what we're going to do is look at the innovation sector, model their effects directly. So you can think of our charter effect then as charter versus traditional public, because we've netted out the effect of innovation schools. Second thing we want to do is take the charter sector and split it by an important dimension of heterogeneity that other people have talked about, which is whether the charter is a mom and pop charter, whether that's just run by folks in Denver, or whether they're part of a charter management organization like Strive, like what we just saw. Are they an organization that runs several charter schools across the city and potentially in other places, okay? So many people have argued that CMO charters are actually more effective than non-CMO charters because they have strong management and governance principles, okay? So how are we going to do that? Okay, so this is what the estimating equations look like, okay? So we have 3 different sectors: CMO charter, non-CMO charter, and innovation schools. We have the score controls for each of those sectors because we can compute those at the school level. So this is our system. Let me show you the numbers here, okay? So the first thing to point out here, so maybe I'll just zoom into this in the interest of time. If I look at my math effects, okay, we said the overall math effect was about 0.5 standard deviations, charter versus not charter. Now I'm going to be doing CMO charter versus other charter versus innovation, all relative to the main fallback, which is traditional public schools. And you see most of the positive effect of charters is coming from CMO charters, okay? So that's broadly consistent with the patterns we've seen in other types of studies, that CMO charters are unusually effective. The innovation sector here is not particularly effective. If you were to just ignore these other sectors, you would come to the wrong conclusion, however. So let's say we were just interested in what is the effect of an innovation school. And there you would ask innovation versus not innovation. You would conclude that innovation schools actually reduce achievement, okay? It's a minus 0.159 standard deviation effect. Not the most precise effect, but The reason it's negative is a lot of children who do not go to an innovation school go to a charter school. Okay, so you haven't directly accounted for that fact when I ask the question innovation versus not innovation. But when I do this multi-sector model, including all of these sectors together, innovation schools don't look as bad. Okay. Let me press ahead and get to one last thing here that we can do with this. So, one thing that people have been quite interested in matching markets is what is the effect of getting your first choice. We can look at that as well. Okay. Again, we have this machinery now. We can look at effects across a number of dimensions. So what we're going to do is take our sectoral models and look at the subgroup of schools, partition them by schools that people have ranked first versus schools that people have not ranked first. So is it the case that people experience larger gains from going to their first choice school versus not going to their first choice school? And I think this is of independent interest because we often evaluate matches by saying X% of people got their first choice. Okay, so you could say that's intrinsically a good thing. That's what people wanted. Is there some downstream consequence that also validates that? And that's what's shown in this table. So again, let's just focus on the first two columns, the math effects. What you see here is if I look at first choice charters versus other choice charters, column 1, there is a first choice advantage. Okay, in Denver, first choice charters improve math performance by 0.4 standard deviations relative to charters that are ranked lower. That effect is only 0.24. If we further unpack that in column 2, I can look at first choice charters that are part of CMOs versus other choice charters and look at the CMO, non-CMO split, and you see that the first choice advantage is primarily coming from the CMO sector. So there are families that experience larger gains from CMO charters that they've ranked first than CMO charters that they've ranked lower on their form. CMO is a charter management organization. So this is like a professional charter school that runs multiple campuses. The type of CMO in Denver, Strive, and KIP is another model in Denver. KIP is the Knowledge is Power program. That's the largest charter management organization in the US. So they would be in this group as well. Sorry? Please, yeah.
What is the difference between charter and non-charter? Are teachers paid more in charter schools?
Teachers are paid less, typically. So the teachers at charter schools are much younger. So in Denver, the way you should think about this, traditional public school teachers, like median age is like 42 to 45. At a charter school, they're more like 30 or 31 years old. So they're not as experienced, so they get paid less. Now, per unit of time, typically, especially at these CMO charters, we see these teachers are working many more hours than traditional public schools, so they're getting paid even less per hour. One reason they can do that is the charters are not unionized, so they're not part of the collective bargaining agreement, so they have a lot more autonomy in their hiring practices and firing practices. And that's a big reason why they're this lightning rod for controversy, charters in the US. It depends who you ask. So there's a segment of young people, like Ariel's son is working at a charter school, who are, I would call them the Mother Teresa types. Okay, they want to go work and with very disadvantaged populations and are willing to.
Because the reason I'm asking is
yeah.
because the charter school take a certain population of teachers from the public schools.
Yeah.
Okay, and maybe they take the better population. So the conclusion is that moving to charter schools is better.
Yeah, so we can say this at the sectoral level.
They simply pull out, in a way, they pull out the good teachers out from the public schools.
Yeah, I think that's a big part of it. I think, in other work on this, not this particular study, this is really about the matching system and how we can use it. The schools that tend to be most effective are those that have a very young teaching core. Many are graduates of the Teach for America program. I don't know if you've heard of that. This is this program that sends, typically high human capital college undergraduates to work in urban public schools districts. They also emphasize pretty traditional educational practices. So the schools in Denver and elsewhere where we've seen these very large effects, they have longer school days. Kids stay till 5 o'clock rather than 3 o'clock. Many of the schools meet on Saturday. Some of them meet in early August when most traditional public schools start in September. So there's that other aspect. I don't think we really know that there's one magic bullet that is the reason for these differences. I think it's this collection of these practices. And a lot of that, I think, comes from the top.
That seems to be a simple question.
I don't know if there will be...
From one to another, then it means that it's not like you have a better organization of the school in a sense. It's just that
I mean, the question is, why isn't that happening right now, right? Why aren't the good teachers going to these schools right now? And I think that's a consequence of the institutional structure a bit, right? So this is, again, kind of anecdotal, right? But several of the teachers that I see at high-performing charter schools start off working in traditional public schools and get frustrated. And so that's, again, because I think they have a lot more autonomy in the charter sector. So I think of all of these things as a downstream consequence of the institutional framework that's been set up with charter schools. This is not to say all charter schools are good. In fact, we see the non-CMO charter schools are not doing so well in Denver. The other thing that I think is key about Denver, just again speaking outside of this paper a little bit, is the structure in Denver is there is one charter authorizer. So the idea behind the charter model was actually Al Shanker, a union guy who proposed charters to begin with. He said, why don't we plant 1,000 seeds and see which ones turn into flowers and which ones turn into weeds? And that was what charter schools were. We're all going to try our idea, and the ones that are weeds, we're going to cut them down. Okay. And whether districts make that difficult decision to actually close down schools and not authorize poor-performing schools varies tremendously by state and region. So in Denver, it's a pretty tough authorizer. I wish I could prove this, but I have a strong view that the authorizer matters a ton. The places that we've seen very strong charter performance typically have a single authorizer. Places where charter performance is much more mixed, they have several authorizers. So right now in the US, there's a big debate about Michigan's charter sector. Our education secretary was formerly from Michigan and did a lot of efforts to support the charter sector in Michigan. And in Michigan, if you and I wanted to start a charter school, we would write down our contract. We would go to the state and say, let's open up a charter school. And they'd say, you guys don't know what you're doing. Go somewhere else. We're not going to authorize this. So what we would then do is go to our local district. And they might say, we don't know what we're doing. Then we'd go to the state schools. Michigan State can actually authorize charter schools. Until we'd find someone who would authorize us. Okay, so there's more than, I think, 60 authorizers in Michigan. In contrast, in Denver, there's one authorizer. In Massachusetts, there's one authorizer. I think that matters a ton. Yeah. Other questions? Yeah, Eric. Yeah.
So here you're comparing charters with charters. Isn't one thing you can do to compare traditional schools with charters?
Yeah. So that's this contrast. Basically, it's charter versus traditional school. In any kind of treatment effect, it's got to be relative to something. So that's the omitted group. So actually, it's more clearly shown here, right? So if you start off with charter versus not charter, about half of the kids who are not charter are in traditional public schools, and then a third are in innovation schools. So we can net out the innovation effect, and then we get this relative contrast, right? So that's where that's coming. But in principle, what you can do is get a single school level estimate. And this is what I would love to see. I mean, cities use a unified enrollment system for placement, and then a year later they go through this process and have school level effect estimates, and that can help facilitate some policy decisions. Ariel?
Two things. One is really just a question. The other is a comment. So, the way you're doing it gets rid of traditional economics in some sense. There's no utility function, there's no production function. So Elkinon's question was really a question of production function.
Correct.
And all the questions about, who's this gaining, or what would have happened if I put in another charter, that all relates to utility function.
I mean, I have an aggregate education production, right? I disagree with something you've already said, so I'll let you go.
So, the question was about the production function. Okay. I think you need a utility function to use this for. I think, though, you should get me wrong.
Yeah.
I do think you're showing effects. The question is, where are they from, and what are their implications?
Yeah.
And so I agree with that.
Yeah.
But there's these next steps about, what. So Elkinon said
That I'm totally with you guys both on. Totally.
On the other side, I don't think you can do any counterfactuals. You can't do any policy until I know what the utility function is.
That I agree with as well. Yeah, I agree with it as well.
I don't really know.
But this is answering the following question. Oh, sorry. Go ahead.
If I was to put in another charter school, I don't really know what would happen.
That's correct. Yeah, and that's a distinct.
I don't know if it would be good or bad or anything else, or where to put it, or what kind, who to attract. So it's not that you haven't shown something.
Yep.
Except we don't know why.
So great. Can I answer now?
Yes.
Okay. So that's true. I have a charter school effect. Where is that coming from? Teachers? Is it coming from longer school days? We'd love to know. My conjecture, based on other work not here, is it's a combination of these factors together. How would we isolate that? We'd have to model the production function. Ideally, we could hold everything fixed except for the teachers and see differences, or hold everything fixed except for the school days and see what happens. Those types of studies don't find effects of this size. That's why I think it's this combination of factors. And unfortunately, I mean, the best evidence on those kinds of studies is survey evidence. Okay, so you look at CMO charters in urban areas versus rural areas, basically hold one thing fixed, change one of these dimensions. So I fully take that point. Now, counterfactual questions, I mean, in general, to answer specific counterfactual questions, we have to write down the model completely, right? And I haven't written down the model here, and I haven't given you a counterfactual question. I've given you a descriptive question, a positive question. What is the effect of these schools on the kids who applied to them, right?
I don't like the word effect. You've shown you've shown a difference between two different groups of people, and you haven't defined who the groups are. Okay? You define the groups by theta, but not by what we care about, which who are they. So that's where we differ. But I do agree that you've shown effects.
So the students that I'm telling you about are these students right here, column 5. So, 71% are Hispanic that I can study using this method. They look pretty similar to your typical charter applicant on observables, okay? And you can go down this whole dimension. I mean, one thing I mentioned earlier is baseline characteristics are pretty close to 0. So this is like your typical kid in terms of baseline. They look like your typical charter applicant. In fact, they look like your typical Denver kid. So I can sharply characterize the population that I'm studying, right? Now, if we do ask a different counterfactual question, like let's double the charter sector, and that is a real question, a lot of states are thinking about that, that's surely going to change who applies to charter schools. So we'd have to think about whether this population would look very different or not, right? And that's a different paper, that's a different question. Yeah. Yeah.
So I agree with Ari almost on everything, but I wanted to highlight actually the promise. So, this is beautiful. Your title is Mechanism Design Meets Research Design. Could we now go do the next step and go the other way around? You rely on this lottery, this tie breaking.
Yeah.
We only have tie breaking because the priorities are crude. Should we now recommend to other institutions to not use a continuous priority system, to make it crude and break ties with lottery so that we can go back and evaluate it?
Yeah, no, that's a great direction which we haven't really explored. I think your intuition is very sensible, which is if we make things coarser and use more lotteries, we can get more variation and learn things. And I've run out of time, but the other paper is basically doing this kind of exercise for non-lottery tie breaking. And one high level, there's 2 high level messages of that paper actually. Let me maybe go to that at the end. Way too much stuff. When you have priorities and non-lottery tie breaking, you learn much less than lottery tie breaking in terms of standard errors. Okay. And there's an interesting mix in systems where you have both types of tie breaking, lottery and non-lottery tie breaking, in the following ways. So a big criticism of research using non-lottery tie breaking is instead of looking at that marginal priority group and those above and those below, you have to shrink your sample to those in the window of the cutoff. Okay. And those kids are by definition special, right? They are the last kid to qualify for a school and the first kid to not qualify for a school. And effects that you get for that population may be even further from a policy question that you're interested in. Now, a lot of policy questions are about changing cutoffs, right? Like affirmative action questions are reducing cutoffs a little bit. So they may not be that far away. But with a match, you automatically get away from the variation, away from the cutoff variation by the same kind of big picture point I want to emphasize. By taking the matching system into account, you get kids who are assigned to a school randomly due to higher ranked rejections. Okay, so suppose I am not the last kid to qualify for the selective school, but I got randomly rejected from a higher ranked choice. I'm getting effects. A way to get at effects is for kids who are non-local. And so that's something that we explore a great deal in the other paper. Another kind of conceptual point that kind of supports what you said is, if you think about priority design, and this came up yesterday as well, and this I think is where this literature is headed, how should we set up these priorities? One thing that I like about lotteries is I think it's easier for consumers to actually judge a school's value added when you have lottery-based tie breaking in their decision making. Because when I have a screen school, the school will look like a phenomenal school. You know, MIT looks like this great school because our students go on to do great things, but that's probably a large part a consequence of the admissions process, right? When it's lottery tie breaking, it becomes more, I think, informative that MIT graduates are doing really well because they were randomly admitted, again conditional on applying. And so we can therefore align productive dimensions of school choices with the decisions that families have to make. So I'm kind of in general in favor of lottery-based tie breaking as a general thing. So let me wrap up kind of where do we want to go, right? So we've talked a lot about this last point. We'd like to think about the steps of other policy counterfactuals, some of the things that Ariel mentioned. So how would I use this together with a model of demand and supply to think about opening up new schools or different patterns of selection if we were to incentivize schools in different ways. We've talked a little bit about pushing this even further. So we looked at sectoral effects by choice. You could, in principle, go down to school level effects by choice, right? So one of the big unanswered debates in the matching literature, I think, are how important are match effects, okay, in schooling. Is it really important to send a kid to his first choice and another kid to his first choice, or is a model much more vertical, okay, that there are good schools and there are bad schools? And then finally, the question that was asked earlier, we know how to do this for deferred acceptance. There are other mechanisms for which we have no idea, including top trading cycles. I think the case for top trading cycles is not as exciting because there's just that one place that's used top trading cycles, but just as a theoretical matter, we'd like to know, as Ori said, is it better to use top trading cycles, maybe for research design reasons, than deferred acceptance or not? And I think that may actually be a relevant factor when you think about which mechanism you want to use. You should be about the allocation and potentially about what can I learn from the allocation. So let me stop there. Thank you very much.